Okay, I think we're ready to start for the second lecture on the physics of ITER.
Thanks, Albert. Morning, ladies and gentlemen. Yesterday's lecture, I tried to give a basic description of a tokamak and describe some of the basic concepts involved in understanding how a tokamak plasma works, how a magnetically confined plasma works. And so I want to build on that today and to start talking in a bit more depth about some of the issues, some of the aspects of tokamak physics, the fusion plasma physics, that make it a very exciting and interesting field to work in, and some of the challenges that we face in turning an experimental facility like ITER into the basis for a fusion power plant. So what I'm going to talk about is, firstly, I'll say something about controlling the plasma. This already brings up some interesting aspects of physics. And I'll talk about the heating systems, current drive systems, which are closely related, how we measure what's going on in the plasma, and about how we put that together into a control system. And then I'll talk about some of the key physics challenges in the areas of confinement, magnetohydrodynamic stability, power and particle exhaust, fusion power in the burning plasma, i.e. what special aspects of plasma physics emerge when you start to heat the plasma with alpha particles. And finally, I'll say something very briefly about the potential for steady-state operation. So let me turn firstly to the question of controlling the plasma. Probably the most important thing to understand about a magnetically confined plasma is that it's in a very complex state. And it can't be created and sustained without a sophisticated feedback control system. There's a lot of free energy available in a magnetic plasma, especially one that's as hot as a fusion plasma. And this is available to generate turbulence. It's available to generate various forms of magnetohydrodynamic instabilities, which are the instabilities that occur in a magnetized fluid. And both the turbulence and the MHD instabilities reduce the plasma confinement. And so if we want to optimize fusion performance, we have to set about controlling them in some way. And so we spend a lot of effort these days learning how to best control the plasma and how to optimize the fusion performance to maintain the plasma in a form where it's capable of producing significant fusion power. When you're actually producing significant thermonuclear fusion power, and this is the transition we're going to make when we go to ITER, there are additional control requirements. It's not easy to handle hundreds of megawatts coming out of a plasma on mechanical surfaces. You certainly can't have the plasma simply sitting up against a surface. The old adage about having a 100 million degree plasma simply resting against the surface, what sort of surface do you design that will take that sort of punishment, is a very simple answer. There's no surface that will take that sort of punishment. So there are special control techniques that you have to develop in order to be able to handle the power, protect the plasma-facing surfaces, and yet nevertheless sustain the plasma so that it's producing significant fusion power. It's an interesting aspect that failures of the control systems lead to conditions which tend to reduce the fusion power or extinguish the plasma. Now, from the safety point of view, that's a very positive aspect. If anything goes wrong in your control system, anything significant goes wrong in your control system, the plasma tends to go out. Good from the safety point of view, not so good if you're trying to produce fusion power to produce electricity. So we work hard at control. So how can we control the plasma? Well, to have a control system, you've got to have a detection system, you've got to have a feedback loop, and you've got to have a set of actuators that make something happen. And so the actuators which we have available in fusion plasmas are firstly the magnetic geometry itself with the massive coils that we have to set up the equilibrium. We can actually manipulate the equilibrium, change the plasma shape, and by changing the plasma shape we can actually affect the confinement and the stability properties of the plasma. In fact, if you look, you can do some quite interesting things with the plasma shape. This shows a range of plasma shapes created in different devices. You can get some quite extreme shapes, such as bean-shaped plasmas. These plasmas, the TCV is the Tokamak, which is just along the road in Lausanne at CRPP. What we tend to do is to take fairly conservatively shaped plasmas like this one or this one, because these have good confinement, stability properties, and they also tend to fill the magnetic field. Magnetic field is an expensive commodity, as I'm sure you know here at CERN. It costs a lot of money to produce magnetic field. And so you want to make the most of it. You want to fill as much of the magnetic field with plasma as possible, because that's your power producing volume. So let me go back. Good. So we can play with the magnetic geometry. Important actuators are the plasma heating systems, and closely related to those, the plasma current drive systems. So you can heat the plasma, you can inject current, you can, by injecting current, you can change the current profile, and that changes both the confinement and stability properties. And these are the two main actuators I'm going to talk about briefly today. You can cause the plasma to rotate. You can actually inject torque into the plasma. You can do this in a couple of ways. You can inject plasma, you can inject particles into the plasma which carry momentum with them and cause the plasma to spin. You can apply electric fields to the plasma, and that also causes the plasma to spin by E cross B drift. And you can fuel the plasma. You can inject particles, and in fact you have to inject particles all the time. But depending on how exactly you inject particles, what rate you inject particles, where you inject particles, you can have impact on the plasma. You can even inject impurities in judicious amounts to help control the plasma, to help, as I'll show, to help control the power output from the plasma. And over the years, we've learned how to use these to influence the plasma behavior. And when we talk about optimizing the plasma performance, this largely means finding the right combination of control tools to keep the plasma in the state that you want it and to produce the level of fusion power that you want. Let's go through here and talk about plasma heating. As I said yesterday, you've got to get a plasma up to temperatures of around 1 to 200 million degrees in order to produce significant amounts of fusion power. Now, Tokamaks already have a built-in heating system, which we call ohmic heating. That is the plasma current itself. As a resistive medium, you pass a current through it, you get ohmic heating. But because, as I illustrated yesterday, the resistivity of a plasma falls as you increase the temperature of the plasma, the ohmic heating becomes less efficient as you get towards the regime where you want to be. And basically it runs out of steam some way short of the temperatures you need. So you have to find other ways of heating the plasma. You have to get the plasma from around several keV, where you can get to with ohmic heating up to temperatures around 10 to 20 keV. There are two basic approaches to heating the plasma. The first is to inject neutral particle beams. Take a beam of protons or deuterons, you accelerate it up to high energy, you neutralize it, inject it into the plasma. The second is to inject radiofrequency waves. Now, this is quite an extensive area. There are actually different forms of radiofrequency heating, as I'll describe, because the plasma refractive index depends on both the density and the magnetic fields, and so there are several different RF options available for coupling to the plasma and for heating the plasma. In addition, each of these heating techniques provides some current drive. Different forms of current drive, different amounts, different efficiencies, different localization. And so choosing which one you're going to use is really a function of what you want to do. There's a further question, and this is a tricky one that we've had to address in building ITER, is how much of each type do we need to optimize the plasma performance? Now, I'll try to illustrate what some aspects of the answer to that question, but in fact it's not an easy question to answer. So let's look at the injection of neutral particle beams. This is actually a very mature technology in current tokamak physics. Basically, you take a beam of protons, a beam of deuterons, you accelerate it up into the region of 100 keV. You then pass it through a neutralization cell, and what comes out the other end is a stream of neutral particles at 100 keV. And that can then pass into the plasma. It has to be neutral, of course, because if it was charged and you tried to fire it across the magnetic field, it would immediately bend in the magnetic field and wouldn't get into the plasma. And so we've got systems that are capable of injection powers of up to 40 megawatts. And these are very effective at heating the plasma, at providing current drive, because you're injecting a stream of particles. As soon as they're ionized when they get into the plasma, they then become a stream of charged particles inside the plasma, and they're effectively an additional current. It's a little more complicated than that, but you get the idea. They also produce fueling for the core plasma, and they produce rotation drive because they're carrying momentum, and so they can spin the plasma as well. And this just shows one example of how effective neutral beam heating can be in existing plasmas. This is an experiment in the American Tokamak TFTR, injecting something in the region of 30 megawatts from memory. What this shows are the densities of the profiles of the plasma density, the ion temperature, and the electron temperature. What you see here is a very peaked central density profile. The center of the plasma is roughly here, very peaked, because these neutral beam particles are filling up the center of the plasma. They're fueling the center of the plasma. So this gives you a very effective fueling. What you also see, which is quite impressive, is that it heats the plasma very effectively. You're getting temperatures in the region of 30 keV here, well into the region for, if it was a DT plasma for fusion power production. Ion temperatures are significantly lower, and about 8 keV in this experiment. This is because at this energy, the beams largely heat the ions. And so this is very effective. It's very widely used in existing experiments. The majority of medium-sized and large tokamaks have significant neutral beam heating powers, and it's a very widely used experimental tool. The catch is that for ITER, to get the neutral particles into the plasma, you've got to increase the energy of the beam significantly. You've got to go from about 100 keV in existing experiments, which is a very well-established technology, to something of order an MeV. And that takes you into a very different technology. And the problem is that here we can accelerate positive ions and neutralize them in a cell with good efficiency, roughly 50% efficiency. Beyond about 100 keV per nucleon, slightly below that, you find that the charge exchange cross-section for neutralization falls off very dramatically. So if you tried to use positive ions for 1 MeV systems, you'd find out that you neutralized hardly any of your particles. The efficiency would be down around 20%. So you've got to go to negative ion source technology, and that's a different technology, much trickier, much newer in our field, and so it requires a lot of R&D. In addition, heating a multi-mega-ampere beam of particles, accelerating a multi-mega-ampere beam of particles up to 1 MeV is non-trivial. And so there's a big R&D program going on at the moment to develop this technology for ITER. In addition, because you're at higher energy, and because the ITER plasma, the total number of particles you need to get into ITER is so much larger, the relative fueling from high energy beams is much smaller. So with these high energy beams for ITER, we face the challenge. Firstly, we've got to develop technology, and that's ongoing. We expect that they'll heat very effectively, they'll drive current very effectively, but we'll lose two things that we get in an experiment like this, which is that we won't get any significant fueling, and we won't get any significant rotation drive. So that's the story on beams. Nevertheless, as long as they do the heating and current drive, they're already making a significant contribution. Turning now to radiofrequency heating, there are three basic schemes for heating the plasma with radiofrequency waves, and these fall into different frequency bands. Ion cyclotron radiofrequency heating is essentially what it says. It's based, it's a magnetized plasma, therefore there's a particular ion cyclotron resonance frequency. It's got a frequency of around, corresponds to about 50 megahertz. So the technology is fairly conventional. It's very, very widely distributed in the everyday world, so you can get the high power technology fairly easily. Could be very effective, very cost effective from that point of view. The catch is that the wave coupling to the plasma is problematic, because certainly these waves will penetrate and will propagate inside the plasma. In a magnetized plasma, as I said before, the refractive index behavior is rather complicated with density and magnetic effects coupled, and in fact at these frequencies, once the wave gets into the plasma, it's no longer a pure electromagnetic wave, but it's got an electrostatic component as well. The difficulty is getting it through the edge of the plasma, because there's an evanescent layer at the edge of the plasma, and you have to get the electromagnetic wave from the edge of the plasma through to this more complex coupled electromagnetic electrostatic wave that's in the plasma. And that coupling is rather difficult. And there's a lot of effort goes into designing antennas that will do that coupling, but it's still an area of research. Second form of heating, radiofrequency heating, is electron cyclotron resonance heating, and this just basically puts the power into the electron cyclotron resonance. For the magnetic fields we work at in fusion plasmas, we're talking about frequencies of around 100 gigahertz, so we're in the millimeter wave region. And the tricky aspect there is, the challenging aspect is that the source technology is non-conventional. Getting multi-megawatt tubes in the millimeter wave region is not easy. Use the technology that's referred to as gyrotrons. Basically, it's an electronic tube in which you have a magnetic field, which you launch in a relativistic electron beam. The electron beam, interacting with the magnetic field, emits cyclotron waves. But it's a technology that's been under development for the last 30 years or so. It works, it's a technology that works. But because the dimensions of these tubes are characteristic of this sort of frequency, i.e. millimeters, you're trying to generate megawatts out of structures with dimensions of millimeters. So it's pretty challenging in terms of power loading inside the electronic tubes. So this is work that's still ongoing. We're able to now build tubes at the megawatt level that'll run for 1,000 seconds. So what we have to do now is industrialize that technology. The technology works, then this is a very attractive form of heating. The coupling is very good because at this frequency, electromagnetic waves propagate freely in the plasma, just like a normal dielectric medium. Absorption is very good at the electron cyclotron resonance and the second harmonic of electron cyclotron resonance. That's not a problem. Space localization is very good because, as I illustrated yesterday, the main field in the tokamak, the toroidal field, has a 1 over major radius dependence. So each frequency corresponds to one radius in the tokamak. So if you want to launch a frequency of 100 gigahertz, it'll be absorbed in one place. If you want to launch a frequency of 120 gigahertz, it'll be launched somewhere else. Also, by steering the beams, you can make use of the Doppler shift as well, and you can use that to vary the space, the position of absorption. So this is potentially a very powerful form of heating, as long as we crack the technology. It's in use in existing tokamaks, but it's turning it into, we want to launch 20 megawatts into ITER. We want it to run for thousands of seconds. That's the challenge. And the third form of radio frequency heating is what's called lower hybrid heating or lower hybrid current drive. It's largely a current drive technology. The lower hybrid resonance is a complex wave resonance in the plasma. It's a combination of the ion cyclotron resonance, the electron cyclotron resonance, and the plasma frequency resonance. So these all come together. There's a complex wave which is partly electromagnetic, partly electrostatic. It has a frequency in the area of a few gigahertz. So this technology is again fairly conventional. You can buy high power klystrons. But again, the problem that we face here is that, as with the ion cyclotron frequency heating, wave propagates fine in the plasma. Outside the plasma, it's an electromagnetic wave. You've got a narrow region at the edge. You've got to couple it through. You've got to get it through an evanescent layer. And so again, the antenna design is the challenge. So that's the pros and cons of the different RF heating systems. Just to mention something about the current drive capabilities, all of these systems have pros and cons in terms of current drive capability, and I'll come to that in a minute. But the reason we want to have current drive is that we want to replace the transformer drive. As I explained yesterday, the current in the tokamak is fundamentally driven by the transformer action. We want to move towards steady state operation. You can't run a tokamak AC. It actually has been done to run a tokamak in an AC cycle, but it's not something you want to do for a fusion power producing tokamak. So you need to be able to run the tokamak steady state, and to do that, you need to drive current in additional ways by what we call non-inductive means, not using a transformer. Secondly, you want to be able to manipulate the current profile to improve the confinement and stability properties of the plasma. And you can do that. And thirdly, there are certain plasma instabilities where you can launch current at a very precise point. This is where the electron cyclotron current drive comes in. You can launch the current at a very precise point and suppress the instabilities. So there's strong motivation to be able to drive current by various means. One of the nice things from ITER's point of view is that when you look at the current drive efficiency, i.e. how many amperes do you get for a certain number of watts of power, you find that it typically increases with electron temperature. And since in ITER we're basically raising the electron temperature by almost a factor of 10 compared to existing experiments, that's going to give us a big leverage in terms of the current drive we can get. The neutral beams, it also increases with the beam energy, so going from 100 keV to 1 MeV is also going to give us a certain advantage. And this is just one result I picked out here. Shows a collection of data from various experiments which shows the current drive efficiency, that is how much current you get for a given power, scaling against the electron temperature in a series of experiments. And it's scaling up nicely as the theory predicts, and should scale to the sorts of levels that we need in ITER. So, the basic message is that we have a lot of the technology in hand to be able to heat the plasma, to be able to drive current in the plasma. There's still a few caveats to that in various areas. There's a big R&D program going on to solve the remaining issues. And our aim is that in ITER we will have a mix of these heating and current drive systems to enable us to do a number of different things with the heating and current drive. It gives a very flexible heating capability, and in particular a very flexible control capability. What we're going to have for the initial stage of ITER operation is we're planning to install 33 megawatts of neutral beam power, 20 megawatts of electron cyclotron power at 170 gigahertz, and 20 megawatts of ICH power. That's going to give us about 73 megawatts. Since we're planning to operate ITER at about 500 megawatts of fusion power with a Q of 10, then about 50 megawatts of this should be adequate to generate that sort of plasma. It's a bit more complex than that, but this is the numbers in the right ballpark. And part of the research of ITER is to find ways of optimizing the heating current drive to make sure that this is adequate. We do have upgrade capabilities, and in the course of the lifetime of the experiment, we could potentially upgrade the power to the region of 100 megawatts if it's necessary. And it probably will be necessary to add on these additional functions about so that we can control all the instabilities we want to control. We can shape the current profile for steady state operation. Why do we need these different heating systems? Well, what I've tried to illustrate in the course of this is that there are different caveats, there are different advantages and different caveats with the different systems. In terms of technology, ICRF and lower hybrid are fairly conventional. You can buy most of the technology except the antennas fairly readily. For neutral beams and ECH, the source technology is challenging, and there's a lot of R&D going on in that. In terms of coupling to the plasma, on the other hand, the neutral beams and the ECH are straightforward, no major problems at all. But the ICRF and the lower hybrid are problematic, and the antenna design is challenging due to this difficulty of coupling the waves through the evanescent layer at the edge of the plasma. In terms of the space localization you can achieve, the magnetic resonance condition favors both the ECH and the ICRF, so you can use them in a fairly precise way to put the heating and the current drive where you want it, whereas the neutral beams and the lower hybrid have more global effects on heating current drive. In terms of the absolute current drive, it turns out the neutral beams and lower hybrid are most efficient, and so for doing steady state operation where you need to drive a lot of current, one of these systems is likely to be the workhorse that provides most of the current you need, whereas the ECH and the ICRF would be used in more specialized applications to control parts of the current profile to suppress instabilities. And so it's because of these different properties of the different advantages and disadvantages of the heating systems, the different applications you need to use them for, that you need to have a range of different systems to heat the plasma. So that's one part of the control system, the actuator part. The other end of it is how you measure the parameters that you need to know in order to control something. And for that we use what we call plasma diagnostics, measurement systems of various sorts. And this is a very interesting area of fusion physics, in fact, because fusion plasmas emit radiation across the whole electromagnetic spectrum, from DC to gamma rays. They emit particles, and so you have a great many different technologies, techniques involved in plasma diagnostics. We have physicists from across a very wide range of physics. This just gives some illustration of the diagnostic capability, some quite limited illustration, but it's just to illustrate different ways of seeing the plasma, looking in different wavelength regimes, and illustrates how you're seeing the plasma at different temperatures. If you look in visible light, and this shows the inside of the jet experiment during a plasma, looking with just with a normal visible camera into the plasma. And what you see here are intense areas here in the bottom where the diverter is, and up here where the plasma is interacting with the wall. And these are actually the cold areas of the plasma. You're actually looking at temperatures of something like 1 to 10 eV when you look at visible light. If you go to ultraviolet light, and now you're looking at various impurities. You get impurities like carbon, tungsten, oxygen in small quantities. You can also add impurities such as argon and neon. In these cases, it's likely to be mainly argon or neon. And what you're seeing here is an intense band a bit deeper into the plasma and down here in the diverter. I'm going to explain later why we try to promote this intense radiation from the diverter region. But what you're seeing here now is still a fairly cool plasma in the region of 10 to 100 eV. It's away from the walls of the experiment, but it's still around the edge of the plasma. If you go, for example, now to measuring the neutron profile, and this shows a neutron profile, 14 MeV neutron profile, measured by tomography from the jet experiment during the DT experiments, what you see here is a very intense spot, of course, in the center of the plasma, because now what you're looking at is the fusion power producing region with temperatures of 1 to 20 keV. And so by choosing different regions of the spectrum or looking at neutron emission, you can see different parts of the plasma. So this gives an overview of how we're going to mount the diagnostics in the ITER experiment. We're going to have about 40 large-scale diagnostic systems. The diagnostic systems are not just used for control, they're also used for protection. If you've got 500 megawatts of power in a plasma and it starts to do something you don't want it to do, you have to know very quickly, because you may have to protect your first wall, for example. And so you need to have diagnostic systems that can tell you something's going wrong and to let you shut down the plasma quickly. And it's also used, of course, very extensively for physics studies. It's how we get the information out of the plasma to understand how a burning plasma works. As I said, we make measurements from DC across the entire electromagnetic spectrum, from DC to gamma rays. There are lots of different processes. At DC, we're looking at close to DC, we're looking at small perturbations in the magnetic equilibrium. As you go up into the microwave region, you're seeing emissions such as cyclotron emission from the plasma. As you go into the visible region, as I showed, you're seeing the very cold area very close to the wall. You then go on through the UV and the X-ray region, you're getting impurity emission from the plasma. And in the gamma ray region, you're seeing some of the nuclear reactions that are going on. And you can measure the neutron emission, and we do, the alpha particle population when we produce it, and various other plasma species, the deuterons, tritons, and so on. We also use techniques called active spectroscopy. That is, we fire in a special neutral beam, and we look at the spectroscopic line emission that comes from the injected ions, and that lets us do some fairly sophisticated measurements. You can actually measure by injecting particles in with the neutral beam, you can actually measure the current profile in the plasma using a rather nice analysis of the polarization of the line emission that comes out. And so the way we mount the diagnostics largely are in these, what we call large port plugs. So this is the ITER machine again. You see the plasma chamber in here. And we have, around the equatorial plane, we have 18 of these port plugs. We have 18 at the top as well, and we have a certain number in the bottom in the diverter region as well. And quite a few of these port plugs are basically filled full of diagnostic instrumentation. They're filled with microwave instrumentation, spectroscopic instrumentation, neutron detectors. We also have diagnostics mounted in the diverter structure down here, and we have magnetic pickup coils mounted around the wall. And just to give you a couple more examples of some of the nice analyses you can do with some of these diagnostic techniques, this shows an analysis of particle transport that was carried out in TFTR, the American experiment, during the DT experiments. Basically what was done here is during the DT experiments, but this was basically measuring on a deuteron plasma. One of the problems we face in fusion plasmas is it's actually quite easy to measure how impurities are transported in the plasma, because impurities have very distinct lines that they emit as they go through the plasma and as they go through the temperature gradient in the plasma. So you can measure that line emission and you can see how the impurities are moving through the plasma. It's much more difficult to measure how the fuel itself, how the deuterium and the tritium is moving through the plasma, because they're fully ionized once they get through the plasma edge. So it's very difficult to measure them once they're inside. And so one of the big questions is how the deuterons and tritons move through the plasma. And this is rather a neat experiment which has started with a deuterium plasma, and they put a small puff of tritium into the edge, and they looked at the 14 MeV neutron signal as that tritium propagated through the plasma. This is the profile of the 14 MeV neutron signal as a function of the radius as the tritium penetrates in. If you invert that signal, they have a vertical array looking down into the plasma, watching the neutron emission. You can do a special inversion on that called an Abel inversion. You get a profile that looks like this. And this is the derived tritium profile. And so this is tritium puff goes in here. So you're seeing that all this tritium is at the edge region of the plasma. And gradually over a period of time, this shows the time scale here. So this is about 100 milliseconds. The tritium diffuses in to the center of the plasma. And so this gives us rather a nice way of actually measuring how the fuel was moving through the plasma. Measuring the fuel particle transport was a big step forward. Somewhat different application is shown here, where we're measuring X-rays now from the plasma. And we have multiple X-ray cameras, and so as is quite common these days, you can do X-ray tomography. You measure the X-ray emission along the different lines of sight. You do the tomography, and you can get an image then, a 2D image of the X-ray emission that's coming out of the plasma. And this shows quite a nice example of how the X-ray emission was used to detect magnetic islands inside the plasma. So the plasma is this region here. The lines here are the flux surfaces I spoke about yesterday. This shows the basic shape of the magnetic equilibrium. And what you see here are some fairly large-scale structures. And these are actually magnetic islands. They're caused by growing instabilities in the plasma. As I'll talk about shortly, one form of instability, one form of MHD instability is what's called the resistive MHD instability. And it's called resistive because it relies on the fact that there is a finite resistance in the plasma. It's small, but it's finite. And that can lead to tearing of the field lines. And the field lines then tear and they reconnect. And when they reconnect, they form large-scale structures, which are magnetic islands, which we call magnetic islands. And these large-scale structures have just like the field lines themselves, have a helical symmetry. If you take a two-dimensional cut through those structures at any point, you see shapes that look like this. And so these are regions where the magnetic structure in the plasma has reconnected. And so this is important because these instabilities can grow to large amplitudes and can lead, degrade the confinement of the plasma. They can even do worse than that. They can terminate the plasma. And this gives us a very good way of detecting that they're there, but also in testing the theory that describes how they occur and how they grow. So that's just to give you a couple of ideas of the power of the diagnostic measurements we have available. So we've got actuators, we've got a lot of measurement techniques, we want to put them together for control. There's a number of different control functions that we need to fulfill. Firstly, there's the plasma equilibrium control, and this is used very widely. I showed you the range of magnetic equilibria we can produce. It's something that's very straightforward. We use magnetic coils around the edge of the plasma, mounted on the wall. We pick up magnetic signals coming from the plasma, and there's an algorithm, a well-defined algorithm, which lets us reconstruct the magnetic equilibrium. And then that signal is fed back to the superconducting coils which control the plasma equilibrium, and we can maintain the shape we want. It's also fairly simple to control the plasma density. Because the plasma is a dielectric medium, if you pass an electromagnetic wave, high-frequency electromagnetic wave through it, it'll be phase shifted. And the phase shift just depends on the density of the plasma. And so you can measure the plasma density using very simple interferometric techniques. And that's how we measure the plasma density, and we can put it into a feedback control system linked to the fielding system. A bit more advanced and a bit more adventurous are what we call plasma kinetic control. In a burning plasma in particular, you want to control the fuel mixture so that you get the optimum fusion power production. You want to control the level of fusion power. You want to control the radiated power because that helps you control how much power is hitting the walls. And that relies on a number of these diagnostic measurements I spoke about. It relies on these diagnostic measurements being fed back into fueling systems or heating systems. And this is an area of ongoing research. For advanced operation, for steady-state plasmas, you'd like to control the current profile. And as mentioned previously, we have a rather nice way of measuring the current profile, and you can then feed that back on the heating and current drive systems to drive additional current where you want it to be. And the final area is the control of MHD instabilities, like this MHD instability I just spoke about, the magnetic island structure here. by taking measurements like that, feeding them back into current drive systems, for example, you can use the current drive systems to basically suppress those instabilities. You can actually launch, with the electron cyclotron waves in particular, you can actually launch current inside those structures, drive current, suppress the instabilities. And that's another area that's a lot of research going on at the moment. So all of these elements have been developed to some extent, but these bottom three are still a very active area of research. We want to basically develop them in existing devices and then apply them in ITER. Just to give one or two examples, this again shows a simulation in ITER of how we'll control the plasma equilibrium from the startup of the plasma at very low current here, expanding the plasma up to higher currents, forming the so-called X-point configuration where we lead the plasma down into the diverter here, and all this is done under magnetic control, and that works very well in existing experiments. The next case is actually quite nice, and it's an example of what I was talking about, using current drive to suppress instabilities. This is an example from the D3D Tokamak. And what we're doing here is, during a plasma pulse, we're measuring these instabilities that I showed you before. The magnetic islands I showed you before grow. What happens, this shows you the plasma, this is actually a measure of plasma pressure in the Tokamak. And so at some point the pressure starts to increase. And as that increases, it generates an MHD instability. And this is the MHD instability signal shown here. It's growing up with the increase in plasma pressure. And it then leads to a reduction in plasma pressure. It degrades the performance of the device. And so what we then do is we turn on our electron cyclotron waves, and we launch these waves into the magnetic structure I showed you before, the magnetic islands I showed you before. And by driving current in the magnetic island, we drive the amplitude of the wave of that island back down to zero. So we actually manage, in an experiment like this, we use electron cyclotron current drive to shut down the magnetic island, and you see when it's shut down, the plasma pressure recovers again. So this is something that's starting to be applied in experiments like D3D, ASDEX upgrade in Germany, and it's a technique that we think we'll be using routinely on ITER. It's a very neat example of feedback control in the fusion plasma environment. So that's basically just to give you an idea of how we heat the plasma, drive current, how we measure what's going on in the plasma, and how we put it all together to give us the control capability we need to set up optimized plasmas in order to produce fusion power. Now I want to talk about a few aspects of the fusion physics that we want to investigate and that we are investigating in existing experiments. And the first thing I'm going to talk about is plasma confinement. I mean, it's an obvious question. You heat this plasma up, what stops it going up to even higher temperatures? What is it? What are the processes that lead to heat flowing out of the plasma? Well, there's a very well developed theory which describes how the heat should flow out of the plasma. It's called neoclassical theory because it's based on the effects I showed yesterday with the particle orbits, where you have some passing particles and you have some trapped particles with these banana orbits. You put that all together, you can do a mathematical description of how these particles interact, how collisions transfer energy between particles, and how the heat leaks out of the plasma. Unfortunately, it turns out that it doesn't do a very good job of describing what's actually going on in the plasma. And it turns out that it's out, in many occasions, by at least an order of magnitude. And the reason for that is that these collisional processes, they do occur in the plasma, but they're dominated by turbulence. As I said before, the plasma has a lot of free energy, and a lot of that free energy goes to drive turbulence. Just as in a normal fluid, if you in airflow you get turbulence generated, so in a plasma you get turbulence generated. And this turbulence leads to a much higher rate of heat leaking out of the plasma. This shows a simulation example. What you're seeing here is, again, a cross-section of the plasma. The simulation is only done in a certain radial region, so the sensor is missing. But what you're seeing here are radial striations, which are turbulent eddies joining up to form radial streamers. And they're basically showing you that the heat is leaking out of the plasma much faster than it should, because the eddies are joining up, forming radial structures. And so this is one of the processes. This is the process that basically means that the heat transport out of the plasma is higher than it should be, or in other words, the overall energy confinement isn't as good as it should be. You can do something about this. It turns out that if the plasma flows, I spoke previously about injecting radiation. It turns out that if there's flow in the plasma, and in particular if there's sheared flow in the plasma, the shear in the flow can break up these radial streamers, as shown in this case here, where we've imposed a rotational shear in the plasma, and it can actually reduce the transport and improve the confinement. And we see this, it actually does happen. But the main message I want you to take away from this is that although there's a well-developed theory, it's not often that we see heat transport that's consistent with that theory, because most of the time what's happening is turbulence is dominating the transport. Looking at a more practical question, if you can't actually write down a first principles theory of how of what the transport processes are, and therefore what the energy confinement should be, how do you go about characterizing the energy confinement? Well, this is an illustration of how we do that. Firstly, I should say it's found that the plasma confinement can actually bifurcate. You actually find for very close states of the plasma, the plasma energy confinement time can suddenly double. And when this was first observed, it was a complete mystery. You'd set up a plasma, you'd get a certain energy confinement time, and then suddenly you'd find that the energy in the plasma was doubling. And this shows an example of this in the jet plasma. It actually shows two things. It shows this fact that one of the things we've discovered in analyzing energy confinement in Tokamak plasmas is as you increase the power input to the plasma to make it hotter, the energy confinement actually goes down. It's a bit unfortunate, but not catastrophic. Just makes it a bit harder to get to fusion temperatures than it should be. And so what this is showing is the energy confinement time as a function of the input power. And it's decaying as you get to higher power. Fortunately, the decay is slow enough that it doesn't stop us getting to the temperatures we need for fusion plasmas. But it shows a second thing. It shows that there's two states possible. This one called the low confinement mode, or L mode. This one, the high confinement mode, or H mode. And what we've discovered is that this improvement in the confinement is associated fundamentally with what's going on in this narrow region called the pedestal at the edge of the plasma. So this shows a cartoon. This is what an L mode profile, low confinement mode profile looks like from the center of the plasma out to the edge. You find that at some point, the transport properties in the plasma edge change, and the temperature at the edge rises up. And then what happens is that you have this profile essentially on top of this reduced transport profile at the edge. And what we've discovered is actually going on is what I showed previously. That is, that we find that there's a rotational shear being set up in a narrow region near the edge of the plasma, and this rotational shear is breaking up the turbulent eddies that normally lead to transport processes. And so when you get enough rotational shear, suddenly the edge temperature goes from the value down around here to this value here. And so this edge pedestal region is crucial to this high confinement mode of operation. So we know how to generate this, how to do this now empirically. We understand a lot about the physics. We still don't have the fine control that we would like, just to flick a switch and say, there it is. But that's something that we're working on. So the main thing to remember from this is that ITER is going to operate in the H mode. We've now been able to establish the conditions for generating this sort of phenomenon reliably and routinely enough that we can make sure that ITER will rotate in the high confinement mode. So how do we figure out what the confinement is likely to be in ITER? Well, if we don't have a first principles based theory, because we can't describe turbulence from first principles, some of our turbulence calculations are getting pretty sophisticated, but we're really not at the level yet where we could run a turbulence code, figure out what the energy confinement time will be from first principles. So what we do basically is we scale. This shows a sequence of experimental facilities from Compass D, which used to be in the UK and is now in Czech Republic, Aztec's upgrade in Germany, JET, a European experiment, and this is ITER. And by carrying out scaling experiments across these different tokamaks and many more scattered around the world, you can develop a scaling of how the energy confinement time changes as a function of plasma parameters, not just the size of the plasma, but other parameters like the plasma current. And what you find is that the energy confinement time basically scales as the plasma current, as the square of the major radius, but it falls off as the input power to the minus 2/3. That's the dependence I was showing you before. And that's a tolerable fall-off. It actually helps us control the burn in fusion plasma. And so this is a set of data that's put together showing how this scaling works across the range of plasmas and predicting where ITER should be. And it's on this basis that we've designed ITER. And it's basically this scaling that says that ITER has to be this big. This is why ITER is this big. It's based on the fact that we've figured out from these different experiments just how big it has to be to give us the energy confinement time we need to get the confinement quality to produce the fusion power. Now I've got a couple of slides on what I call the ITER physics bases. On a basis of a few simple rules like that, you can actually write down the basic constraints on designing a Tokamak experiment, fusion power producing experiment like ITER. I'm not going to go through them, it's a lot of detail, but it's there if you're interested. Let's go back to this question of MHD stability. As I said, the interaction of the plasma fluid and the magnetic field is described by MHD theory, magnetohydrodynamic theory, and this actually provides a very good qualitative and in many cases significant quantitative description of stability limits in the Tokamak. And it also describes many of the instabilities that we've seen in Tokamak plasmas, in fusion plasmas. There's two basic types of instability, so-called ideal instabilities. These are instabilities which lead to field line bending. They twist the magnetic field to cause it to bulge. They don't actually tear the magnetic field and create magnetic islands. These instabilities, in principle, can grow very rapidly because they're simply bending the magnetic field. And perturbations in the magnetic field can propagate very quickly. The characteristic time scale for a machine like ITER is less than a microsecond. So you can, if you twist the magnetic field in ITER, the propagation time is very fast. So the ideal instabilities are ones that you have to be careful about because they can, in principle, grow so quickly there's nothing you can do about them. Fortunately, there's not too many of those. Resistive instabilities cause tearing and reconnection, and these lead to the formation of the magnetic islands I spoke about before. This is actually a simulation in this case, showing again structures here where the magnetic field lines have torn and reconnected, and you have a large magnetic island here. This is what we call, these magnetic islands have symmetry around the torus. They're associated with particular values of the Q profile. The Q profile I spoke about yesterday was the safety factor profile. And when this Q factor takes on integer values, 2, 3, 4, or low rational values such as 1.5, 2.5, and so on, these islands can grow. These are particularly susceptible. And so this is the case at the Q equals 2 surface where we have an island which is a twofold structure in the polar direction, and it's also got a helicosymmetry with one node toroidally, so it's called the 2-1 mode. So these tend to grow on a slower time scale. They grow slowly enough that you can actually apply techniques to correct them, such as the technique I showed, the ECCD I showed before. One thing I should mention is disruptions. The disruptions are probably the major reason we're worried about MHD instabilities. MHD instabilities can be relatively benign. They can go to a certain amplitude and just sit there happily degrading the plasma confinement so that performance isn't as good as it should be, but it's not catastrophic. But if they grow too large, they lead to what's called a disruption. And a disruption is very simply a very fast event that extinguishes the plasma current on a time scale of milliseconds or tens of milliseconds. And that's a pretty unpleasant event, particularly when you extrapolate it to the ITER scale. In the ITER plasma, you're going to have 300 megajoules of stored energy. You're going to be carrying 15 megaamperes of current. If you snuff that out in a few tens of milliseconds, all of that energy and all of that magnetic energy has got to go somewhere. And it's going to go onto the walls. And that's a lot of energy that's going onto the walls. So a disruption can be a fairly severe event. It leads to very large heat loads on the plasma-facing surfaces. It leads to significant electromagnetic forces in the vacuum vessel. And it can also generate large energetic runaway beams. You can convert this 15 megaamperes can be converted into up to 10 megaamperes of 10 MeV electrons circling in the plasma. This shows a cartoon of what a disruption is. What happens is that at some point, one of these instabilities I've been talking about can start to grow. If you don't control it, it leads to a return from the H mode to the L mode, it continues to grow, degrading the plasma confinement all the way, and then at some point it gets large enough that it basically expels all the energy from the plasma. And this event can be very fast. It can be 1 or 2 milliseconds. You can be losing 200 megajoules in 1 or 2 milliseconds. And all of that has to go onto the walls. Because the plasma suddenly gets very cold, you're taking it from a temperature which might be several keV down to a temperature which may only be a few eV. The plasma is simply so resistive it can't carry the current anymore. So the current starts to decay, and it decays typically on a time scale of tens of milliseconds. All that magnetic flux has to go somewhere, and what it tends to do then is it drives current in the walls, in the vacuum vessel that's surrounding the plasma. So this 15 megaamperes that was previously in the current, in the plasma itself, can appear in the walls of the vessel. And if you've suddenly got 15 megaamperes or 10 megaamperes flowing in the walls of your vacuum vessel, you have very large electromagnetic forces. And then, as a result of processes which I won't go into here, in this current decay phase, because the current is decaying very rapidly, it's generating a high electric field, it can accelerate a small population of electrons to high energies. So this is something we routinely see in existing experiments. The energies and the magnetic current, the currents we're dealing with are much lower. So it's unpleasant, but it's not catastrophic. At the ITER scale, it would be a very serious event. And so we've got to find, so this is one of the reasons we've got to control the MHD instabilities that are responsible for these events, and we have to find ways of mitigating the disruptions. And that's something that we're working on. There's a couple of other areas of MHD stability that I could talk about. There's not a lot of time. Let me just talk about one of them, which is the question of plasma pressure. Plasma pressure is important because, as I showed yesterday, the fusion power depends on the plasma pressure squared. It's that simple. So the higher the plasma pressure, the more fusion power you get out. And it turns out you can't make the plasma pressure arbitrarily high. As you make the plasma pressure higher, the kinetic pressure of the plasma starts to push on the restraining magnetic pressure being produced by the magnetic fields, and the free energy then starts to give rise to various forms of MHD instabilities. So as you get to certain levels of plasma pressure, you start to generate MHD instabilities. The relevant parameter is this beta parameter, which is the ratio of the pressure, the kinetic pressure to the magnetic pressure. Typically in a tokamak, it's a few percent. You can get up to around, as shown in this graph here, you can get values up around 6 or 7%. This magnetic field here is the toroidal magnetic field. It's been shown that the right way to normalize this, to measure this, is to ratio this beta against the plasma current divided by the minor radius times b. If you do this, you can pull all of the results from different experiments together, and it forms a very nice description of the stability boundary. And what you find is that typically this beta normalized has a value of 2.8 to 3.5. This is what's called the Troyon limit, after the physicist who developed it, who happened to be the director of the lab at Lausanne in the past. But what this basically tells you is, when you convert it back into these real numbers, is it gives you a number in the region of 5 to 6%. So it tells you the maximum pressure expressed in terms of the magnetic pressure is about 5 to 6%. And if you exceed that, you get various forms of MHD instability. So there is a limit to plasma pressure. It's set by MHD instabilities. We can do something about it up to a point, but at some point you generate, as I said before, an ideal MHD instability, and that then sets a hard limit as to the maximum pressure you can get. Let me turn to a different subject, which is a particularly important subject for when you're producing fusion power, and that is how you handle the power that's coming out of the plasma, and how you also handle the particles that are flowing out of the plasma as well. This shows a cartoon of the problem of power and particle exhaust. You have the core plasma, which is generating, in the ITER case, we hope 500 megawatts of fusion power. Now, fortunately, most of that fusion power is going out in the form of neutrons. As I showed you yesterday, 80% of the power is in neutron power, so it goes straight out of the plasma and is absorbed by the blanket on the wall. So that's fine. It's absorbed in the structure. It's not a surface absorption problem. It's absorbed in the structure, and we can deal with that. What's left behind is the alpha power, which is 100 megawatts, plus the heating power that you're using to generate the plasma initially, which is about 50 megawatts. So you're trying to deal with about 150 megawatts. You just can't have the plasma sitting on the wall for reasons which are, to describe in detail, are a bit complicated. But it doesn't work, basically. So the heat and the particles are going to flow out of the plasma into what's called the scrape-off layer. These are what's called closed flux surfaces. They're closed on themselves, so that means that the particles run around the torus on these surfaces, and they have to diffuse across the surfaces. Once they get onto this external region called the scrape-off layer, these are open flux surfaces. And then the particles which are running along the field lines are directed down into this structure called the diverter at the bottom of the tokamak down here. And we try to take most of the heat power in this region down here. We have special high heat flux surfaces, so the power flows with particles across into the scrape-off layer down into the diverter. However, the problem we face is that, try as hard as you like, the best you can engineer are surfaces to handle about 10 megawatts per meter squared. Now you've got 150 megawatts. You lose some radiation, so it's more like 100, 120 megawatts coming out of the plasma. It's flowing down the field lines. This area that you have down here is only a few square meters, in fact. Even when you extrapolate it around the torus, it's only a few square meters. So you're having to deal with something like 40 or 50 megawatts per square meter. So this is a problem, because the best you can engineer is about 10, in extremis 20 megawatts per square meter. So that's an issue you have to deal with, and I'll describe how we deal with that. You also have to extract the helium. The alpha particles are just helium ions. When they slow down, they're just helium nuclei. You have to get them out of the plasma, or they build up and they eventually poison the burn. At the same time, you have to prevent impurities from the walls getting back into the core of the plasma, because there are plasma particles escaping. It's bombarding the walls, it's bombarding the diverter, and the impurities that are generated by that bombardment can get back into the plasma and can shut the plasma burn down. And you also have to ensure that the plasma-facing surfaces last sufficiently long. They've been bombarded by plasma particles. If they're eroded too quickly, you have to keep shutting the machine down, replacing the surfaces, starting up again. It's not the way you want to run a power plant. So you've got to limit the rate of erosion to something that's acceptable. So this is part of the way that we do it. This is just give you an idea of what a diverter really looks like. This is one of the ITER diverter cassettes. So in cross-section, this is the structure I showed you down in the bottom of the tokamak. There are 54 of these that are mounted together to form the complete torus injet in ITER. The function of all the structures is a bit complicated, but basically down in the bottom of this structure here, you have high heat flux handling surfaces. You have surfaces which are engineered to take 10, in extremis 20 megawatts per meter squared. It also has slots that you can't really see in this structure that allow particles to leak out behind the diverter, and behind the diverter you have cryopumps, and the cryopumps pump hydrogen, deuterium, tritium. We use activated charcoal, so they also pump helium, and they also pump impurities. And so the diverter is the key element in helping in controlling the power exhaust and controlling the particle exhaust. But with this limit on the power handling capability, it won't do it all by itself. And so what you do is you develop what is called a detached diverter. And what we mean by a detached diverter is that the plasma at the diverter is so cold that even though it's touching the diverter, it's effectively not touching the diverter. And by the time you get to the diverter, you manage to cool the plasma to such a level that there's basically not a real plasma interaction there. And the way you do that is you inject impurities into this region just above the diverter so that you radiate a large fraction of the radiation. And you remember this picture I showed you earlier when we were talking about seeing the different temperature regions in the plasma. The middle one I showed you was a case like this where we'd injected impurities in, and you have a very highly radiating region down here, and you also have a cold shell radiating around the outside. Now the advantage of radiating the power is the power is radiated over 360 degrees. So you're effectively, through radiation, you're spreading that power around the whole wall, but you're spreading it around the wall without the plasma itself interacting with the wall, which is the key concept. If the plasma interacts with the wall, you have very energetic particles bombarding the wall. If you radiate the power, if you can set up a situation where most of the power is radiated from the edge of the plasma and from the diverter, it's radiation that's impinging on the wall. And then the power handling problem becomes much simpler, because the area of the wall is more than 500 square meters. Remember, it's about 680 square meters. you have 120 megawatts coming out, you've got less than a megawatt per meter squared to handle. So this is the physics of how we handle the power, basically through converting the plasma power into radiation, which is then spread over the walls of the tokamak. Last issue I want to touch on in the area of plasma power exhaust is the question of plasma-facing components. From this description, you can imagine that the plasma, what you actually use to face the plasma has to be pretty special. We use a mixture of materials. Down here in the high heat flux region, we've traditionally used carbon fiber composite materials because it's got very high thermal conductivity, which is good for conducting high heat fluxes away. It's also got very good thermal shock resistance. It doesn't melt, it sublimates, and that's easier to handle. So that's been what we've commonly used in experiments. One downside of it is that it combines chemically with hydrogen. Not really a problem in existing experiments when you're working with hydrogen and deuterium, but when you're working with tritium, what that means is if the carbon combines chemically with the tritium and the carbon, and it then forms deposits around the bottom here, you're tying up a lot of your tritium in the bottom inside the torus. You can't get that tritium out anymore. And that's not good from the radiological point of view. It's not good for your tritium economy. So I'm going to tell you what we're going to do about that. The first wall is lined with beryllium, which is a very light metal, very low Z effective. It's got good thermal conductivity. It's got a low charge, and that means that it doesn't radiate much if it gets into the plasma. And that's an important property for the first wall. And then a lot of the rest of the divertor, that's not the high heat flux region initially, is clad with tungsten. This is a good material from the point of view of its high melting point and very high sputtering resistance, got a very high sputtering threshold. There's still a concern about it that it might melt during thermal transits. I haven't had time to talk about thermal transits except the disruption. It's one of the issues that if you get a disruption, there's enough energy that you might even melt tungsten. And that's why we've got to solve the disruption problem. Once we've solved that problem, we intend to use tungsten to replace the CFC, because this problem of tying up tritium inside the torus is a serious one for a nuclear device. And so eventually this divertor will be totally coated in tungsten. Let me say something very briefly about bonding plasma physics. When we talk about bonding plasma physics, we mean that the plasma physics associated specifically with having a DT plasma, having the alpha particles produced by a DT plasma. There's a number of areas of research that this opens up. Firstly is the question of do you confine the alphas in the plasma, which is an important question. The simple answer is yes, we're pretty certain you do. There's the response of the plasma to the alpha heating itself, because this will become the dominant form of heating. We'll no longer be using the external heating systems dominantly, we'll be using the alpha particles. And the third is the influence of the alpha particles on the magnetohydrodynamic stability. We've already got some insight into these questions because in existing devices you do get energetic particles. We've already had the DT experiments in JET and TFTR, which give us some information on alpha particles. But the heating systems I spoke about, particularly the neutral beam injection, already generate energetic particle populations that are significant enough to give you information on how these non-thermal particle populations behave. And what we find is that these energetic particles, including alpha particles, are well confined in the plasma. We find that they interact with the background plasma as predicted by theory, and they transfer their energy to the background plasma as predicted by theory. So that's important, because if we're going to use alpha particles to heat the plasma, it better interact the way we expect theoretically with the plasma and heat the plasma. But on the other hand, there's a form of MHD instability, which I don't have time to talk about here, called alphane eigenmodes. These are a particular form of bending structure in the magnetic field, is the best way I can describe it, which can be excited by the alpha particles because they have such a high velocity. However, from the experience we've got in existing devices, for either parameters at Q equals 10, the impact of these instabilities is likely to be tolerable and not a concern. Just to give you a little bit of information on some of the energetic particle population studies done in existing experiments, you can show, it's fairly simple to show in fact, that as long as you have a plasma current of around 3 megaamperes or above, you'll confine 3.5 MeV alpha particles. And so that's important, because it means that the plasma we need for ITER is not determined by the plasma you need to confine the alpha particles, but by the confinement. We know that we need to scale ITER according to the confinement, and not, once you've decided you have to build a 15 megaampere device to get enough confinement, you know you're going to confine the alpha particles. These experiments in existing devices have validated the classical slowing down of fast ions on the background thermal plasma. We've done experiments over the range from 30 keV with neutral beam injection to 3.5 MeV alpha particles. This shows the ratio of the experimental value of the slowing down time against the theoretical value across the variation of the slowing. This slowing down time is essentially a substitute for the energy of the particles, and you see that it's very close to 1. Error bars are moderately large, but it's close to 1. So the particles are slowing down as we predict. And so that gives us confidence that when we produce the alpha particles in ITER, that they will actually heat the plasma. Another experiment, which is a nice experiment done in JET, is to show that alpha particles do actually heat the plasma. We know that energetic particles heat plasmas because we inject neutral beams, the ion cyclotron heating accelerates the energetic particles, so we're confident that energetic particles heat plasmas. But it's nice to know, it's nice to have a feeling of security that alpha particles also heat plasmas. The population in JET was pretty small because they only produced about 16 megawatts of power, but nevertheless it gave us a very clear indication that the alpha particle is heating the plasma. One thing you have to understand is that because the energy of the alpha particles is so high, you predominantly heat the electrons, not the ions. It's not as big a problem. Now, it's the ions that are doing the fusion reaction, so that you might think at first glance that's a bit of a concern. It's not such a big concern because at the densities we're operating at in these plasmas, the electrons immediately transfer a lot of that heating power directly to the ions. So the ion electron temperature is very close in a device like ITER. But the actual physics that's going on is that the alphas are transferring the power to the electrons, and the electrons are then transferring it to the ions. And so what this shows is is an experiment that was done in JET to show how the alpha particles were heating the electrons. Difficult to measure directly on the total energy content the effect of the alpha heating, because the alpha power is such a small fraction of the total power in these cases. But by measuring the effect on the electrons, it was possible to show that the alphas are doing the heating. And this is a series of experiments that vary. It's quite interesting. What happens here is you start off with no tritium at all, so it's a pure deuterium plasma. You increase the tritium concentration until you get something close to the optimum 50 or 60% tritium, and then you increase it till you're close to 100% again. And so what you see here is the electron temperature goes up, and then it comes back down again. And that's because if you've got 100% deuterium or 100% tritium, you're not producing any fusion reactions. When you've got 50% deuterium and tritium, you're producing fusion reactions and you're producing alpha particles. And what you see here is you get the highest electron temperature when you are producing the alpha particles. And so this is a nice demonstration that the alphas are actually hitting the electrons as we expect. I won't talk about the alpha eigenmodes. There's a slide there you can look at if you want. Let me just say something about steady state operation. Last thing I want to mention. Because ultimately we want to drive a tokamak in steady state, because if you're building a power plant, you want the power plant to run in steady state. You don't want the power plant shutting down every hour to regenerate the transformer, recharge the transformer in the tokamak and start over again. And so to do that, we've basically got to replace the transformer action in the tokamak by external current drive. And there are two elements of this external current drive. One I described here today is the current drive that you get from additional heating systems like neutral beams or lower hybrid or electron cyclotron. The other I described yesterday is what I called the bootstrap current. It's the current that you get because of the pressure profile in the plasma. And if you put these two together, there is actually the possibility of getting enough current drive that you can drive 100% of the current in the plasma purely with these non-inductive means, and you can turn off the transformer. And that's a significant aspect of the research that we're doing now and the research we want to do in ITER. I won't go through the details of this. You can read it for yourself. Basically, what it involves is you have to set up a very special type of plasma with particularly high confinement, where you have this transport barrier at the edge that forms the H mode. You also generate a further transport barrier inside the plasma, so you've got even higher confinement than normal. This lets you get to very high pressure plasmas, still inside the beta limit, but high enough pressure that you can generate a lot of the bootstrap current. So you might generate as much as 50% of the current with this bootstrap effect. And then the other 50% you drive with the external current drive. And if you do that, you can in principle set up a steady state. Just to show you very quickly, this shows the electron and ion temperatures that's been simulated for ITER. This is a simulation of ITER based on experimental results we've got from existing devices. What you see here is this very steep gradient in temperatures, which is the internal transport barrier. Because of this very steep gradient in temperatures here, it's a steep pressure gradient, you get a very high bootstrap current, which is shown in red here. So this is the bootstrap current contribution to the current profile. This is the current contribution you're getting from a combination of neutral beam injection and lower hybrid current drive, and this gives you the total current profile. Now what's interesting about this is that when I showed you a current profile yesterday, the current profile was peaked on axis. But in this special type of regime that we set up for steady state, it's peaked well off axis. And this is part of the trick to getting this special type of internal transport barrier. And so this is, in a sense, the extreme case of plasma control, where you put all the elements together to control the current profile in a way that controls the pressure profile that allows you to drive the current to give you steady state operation. And we're still not there yet. There's a lot of research going on at the moment, but it is the ultimate aim of the experiment. So the last thing, what I've been trying to show in the course of this talk is the fact that ITER has a lot of flexibility. We've built in a lot of capabilities in terms of the measurement systems that we have, in terms of the actuators that we have. We can play a lot of tricks with this plasma. We can do a lot of interesting things with the plasma. And we've got the prospect of doing, not just producing fusion power, but actually of doing a lot of very interesting plasma physics in the course of it. And so I put together a very short list of references that you can have a look at if you're interested in following this up. Thanks very much for your patience.
Okay, we have a bit of time if there are questions, and this is your occasion because David already has to rush back tonight to Cadarache. So if you have questions, this is done.
It was a very nice talk and explanations. What I missed a little bit in the end is how do you actually get the energy to do something good for us? You have explained that 80% of the energy goes by the neutrons to the walls. You have a hard time to get the energy from the diverter. Yeah. So where in the end you get the energy to produce something useful for normal energy?
I didn't go into that because I'd be stealing my colleague's story. Gunter Janishitz is going to tell you in great detail about things like that, but let me very briefly describe it. Basically, you use all of the energy. In the end, you use 100% of the energy. You get the 80% that goes up to the walls and the neutrons, and you recapture the energy that's coming out of the plasma anyway, and that does end up in the walls. But what you're going to do in a reactor is that in the walls of the device, you'll have a coolant flowing. It's basically, in a sense, just a very sophisticated boiler system, like a coal-fired plant. So the power that's coming out of the plasma will be absorbed by the walls. It'll be absorbed by the coolant in the walls, which may be water or maybe helium gas. You'll take the coolant, the hot coolant, it sounds like a contradiction, off to a turbine or a heat exchanger in the first instance. You'll then use the heat from the heat exchanger to drive a turbine, just as you do in a conventional power station.
That's basically the whole surface.
The whole surface basically